And that's an example of a smart material that has seen what we call training to allow for a two-way shape memory effect. We have done some work on 3D, 4D printing of stents. So this is one of my current projects looking into printing of shape memory alloys used in arterial stents. So as we all go old and our arteries start to be filled with plaque and other things, which is caused by bad lifestyle, smoking, and eating unhealthy food, so we get something called stenosis. And that stenosis basically needs to be addressed by a cardiologist by putting a stent to open the flow for blood to proceed in all the arteries. So the idea we came up with was, why don't we try to print those stents out of those smart materials? We compress them, put them inside the heart, and then we'll open up and open the shape for the arteries for blood flow again. And these are some of the stents that we've been printing using our metal printer machines. They're made, as I said, out of a nickel titanium shape memory alloy. We've done some work on their compression and testing and so on, and we've also done some testing to test how they would behave in a blood flow. So we put them inside a system that has a water, and it will pulse the water waves exactly like what you do in blood, basically, to see what happens when you put them inside the blood or in the artery, and if they can reopen the artery. So we did a lot of studies to look into their printing, and by using a process called the laser powder bed for printing of metals from metal powders. And as you can see, you don't see any defects inside. They are all entirely solid and clean. Unfortunately, the surface is not that uniform, and that's because the metal powders that are used for printing, they may stick sometimes to each other, generating a slightly ugly kind of shape. But that depends on the geometry you are printing. If you print a shape like that, the zigzag shape, you may get some non-uniformity in the shape. But if you print some other geometries, you can get easier stents. Yes, you still have unmelted particles on the surface, but these unmelted particles can then be cleaned to create a more uniform stent. So what we have been doing is that we have been using chemical etching to clean the surface, and we found that that again depends on the geometry. So if you print a straight stent similar to that one, with etching, you can clean up the surface and generate a nice looking stent like that one. But if you try to print a shape which has those zigzag stents, usually also would get some zigzag surface finish, which of course would be unsuitable for implantation inside the arteries. So this pushed us to think about the need to basically design the stent in order to make sure that it can fit within the application we want to have, which is arterial stent. So those stents, when compressed, they will be put inside the artery, they will open up again and allow the blood flow to continue. I'll talk now about another shape which we have been printing also out of shape memory alloys, which is known as the auxetic shapes. These auxetic shapes and geometries, they have a negative Poisson's ratio, so which means that if you apply load into them, they will be short and small. Usually, if you apply load into a common engineering shape, they will become short and fat. This one will become short and it will basically close inside and thin. And those shapes, they also have a very interesting, load shocking or load absorbing behavior. So if you apply load into them, as opposed to structures which will basically move aside when you apply load into them, those materials, the auxetic shapes, will have the material will move together to close and resist that movement. And the concept we wanted to make out of shape memory alloys is basically we wanted to look into making armor material that can resist shocks. So essentially, when you hit it with a shock, it can stop the bullet rather than penetrating through it, or rather than penetrating through it. So it makes it a much lighter shape, much easier to print, and also having the ability that after the compression, if you apply hot air into it, the bullet will be basically ejected outwards after you finish, after the compression or after the initial shock from the projectile. So we did a lot of studies trying to optimize the geometry, which is really important. If you want to design the Poisson's ratio of the material, you can play with the design of the unit cell. So these are different unit cells based on the angles, based on the amount of material inside. that can control your Poisson's ratio, so you can achieve a Poisson ratio of almost -2. Or if you play with the amount of material you have inside, you can do the same thing. You can also control the amount of Poisson's ratio by controlling and making them either thinner or slightly thicker like that. So we've done that, and we've looked into the shape, and we managed to print some nice geometries by controlling the geometry, adding the right amount of material inside, and that was able to give us the level of Poisson's ratio we are expecting. And at the end, the printed shape was printed and tested to see how it will behave upon loading and how it will close upon itself when a load is applied into it. So that's, again, it's a type of a shape that will apply for a load, and then if it gets heated or so on, it will open up again. If the material you print is super elastic, it can even return back to its original shape once the load is removed. We also did more work on those class of materials, and that's probably my last case study, looking into using these shapes for medical implants, where we printed, in this case, structures that tries to echo bone cells. So what you can see here is that the bone cells in general, they have variation in density. So they can be dense from the outside, less dense from inside. So what we had in mind was, why don't we try to create, using that interesting material, a material that is graded in its density from the inside to the outside. So it will behave and absorb the shock in the same way as bones, and it will also have the same elastic modulus as bones. Healthy bones usually have an elastic modulus of around 30 gigapascal, but that modulus would drop a lot as people get old with osteoporosis and things, to be sometimes even up to 5 gigapascal or even less. So when we looked into making shapes, we looked into making more than one shape. So we looked into making uniform lattices, and those people, sometimes people call them nowadays metamaterials or meshes or lattices. So those lattices, as you can see, they have an engineered porosity inside them. Or you can create a graded lattice where the density will change from the outside, where it's more dense, to the inside, where it's more porous, as you can see. And we applied a mechanical load into it. And what we found that in a uniform lattice, usually you will have, this is a strain map to show how deformation happens. We had that kind of 45-degree profile of a strain map when a load is applied. But when we applied that on a graded lattice, we saw some sort of like a central shrinkage in the strain, potentially looking like how you would squeeze a sponge, how you apply a load into a sponge. And that basically resulted in also a much lower elastic modulus, reaching sometimes into around 4.6 down to 0.75 gigapascal. So that managed to generate a very low modulus material that is actually very close to human bones, and it's also a biocompatible material from that point. Now, I will come to the most important part in my talk, which is, from all of these things, they raise a lot of opportunities for work and for a collaboration. And I would like to use this chance as a call out for collaboration with many of you in different parts of the world. So our machines are always running 24/7, the metal printing machine. And there's always a chance we can make some extra samples from the materials we use if you are interested. We can even make them interesting by making them in a lattice shape or build them out of a smart material or control their properties and behavior. So the current property opportunities we have in my group include magnetic materials, especially magnetocaloric materials. Those are materials that transform magnetic field into temperature effects. We also play with permanent magnets, and you can see there's a magnet here printed and stuck into a piece of metal. We've been printing also smart shape memory alloys and Heusler compounds. We're also interested in to look into quasi-crystalline alloys or batteries or materials used in energy storage. All of that is of interest to us. So if you are interested, just drop me an email and let's use this as an opportunity for collaboration. Finally, I'd like to thank you for the invitation one more time, and I would like to thank those who have been doing the work, my group and my PhD students in Birmingham. And thank you again for the invitation.
Thank you very much, Prof. Matters, for your inspiring very wonderful presentation. I would like to, I have few comments in the Q&A, but not questions per se. Two people are asking if you would be willing to share your PowerPoint slides. I'll give you room to answer to that. But I would just like to have a quick recap on Prof. Moata's presentation. He started with the 3D printing hype. For me, someone who is also in the field of additive manufacturing, I quite understand Prof. Matters when he started with talking about the hype when this technology was invented, and there were a lot of hypes in almost all sectors of the economy and in the industries as well. And then further to that, he alluded to 4D printing, which is now the in thing. That is where the technology is going, wherein materials are now being a lot of research is now being conducted into how 3D printing can now be 4D, wherein materials are able to respond to external stimuli, time-dependent functionalities and all of that. And he also spoke about smart materials, micro 3D printing, and also shared a couple of his work, so a lot of case studies regarding a number of the work that he is doing at Birmingham. I have visited his facility. I'm actually really intrigued with the work that himself and his team are doing at the University of Birmingham. And I'm looking forward to the pandemic being over, borders open, and when next I'm in the UK, I promise that I'll pop in again to hopefully I'll be able to catch you this time around.
Yes.
And yeah. So thank you very much for your wonderful presentation. So
thank you. I'll make the slides available, so I'll send it to Professor Amal Amin to send around. That's not a problem at all.
All right, thank you very much.
If anybody wishes, I'll leave my email in the inbox as well. If anybody will end up in the questions in the chat box, so that if anybody wants to drop me a line, please feel free to do so.
Thank you very much. I was actually also going to ask that you talked about collaboration and all of that, and I was looking at your last slide if I was going to see your email address in there for people that don't know you. So I think, yeah, in the chat box, you can please leave your email address in there so that people can contact you for collaboration and also for to be able to work together moving forward. So yeah, I'm still waiting. Is there any hand up? We don't want to have people speak. We prefer that we use the chat box. And is there any one quick question for Prof. Matters before we move on to the next presentation? At this point, the two people that left comments in the Q&A were asking for copies of your presentation. So yeah, at this point, I don't think you have any question from anyone, but the floor is still open. We can use chat box. We can also use Q&A. So I think without wasting time, we should move on to the next presentation. I'm moderating this session, and I also happen to be one of the speakers in this session, and I'm the second speaker, and I will be speaking on sustainable Mother Earth, and I am urging myself and each and everyone as researchers to play our part. So I hope I'm able to share my slides. I'll do that quickly, and then I'll move on to my presentation. And as I move on in the presentation, please, for new people joining us, remember to introduce yourself in the chat box. If you have any question for either Prof. Moata or I, please feel free to leave those questions in the Q&A. And after my presentation, I will do it to answer my own question. Prof. Moata still also will have the floor to be able to answer his own questions as well. Please stay with us. I see 38 participants. We also look forward to many more people joining us in this session. I'm now sharing my slides. I hope you can see my slides. Can you see my slide?
Yes, it's okay. Yes, Prof.
All right.
You can just continue. Yes.
Okay, thank you. Thank you very much. So, yeah, currently serving as the director of the Pan-African University. It's a university that is backed by the African Union. We have 5 of these institutes across the African continent, and I'm heading the West African hub located in Ibadan, Nigeria, hosted right inside the University of Ibadan. So, like I said earlier, the title of my presentation is Sustainable Mother Earth, Consciousness regarding making designs as an engineer to regarding looking into sustainability of the process and how it affects the earth. I would like to start by thanking Prof. Amal Amin, who invited me to give this talk at this conference. And I've had interaction with her and with I've also collaborated with the Women in Science Without Borders. I recall hosting a conference at the University of Johannesburg, and these were photos during that conference. You can identify Prof. Amal Amin there in the picture, and that's myself also in the pictures as well. So thank you for the invitation to Prof. Amal Amin. I'm not sure if she's able to join this session or she's in the other parallel session. So this is the outline of my presentation, a brief introduction, some basic concepts relating to the topic I'm speaking about, some personal contributions regarding my research footprint. I'll talk about Fourth Industrial Revolution, on what we are doing on the African continent and as it affects the Mother Earth, and I will summarize. So I'll start with the slogan of IBM that says that let's build a smarter planet. Let's build a smarter planet to IBM some few years ago has to do with having to manufacture, to produce, to have products that will have very, very little less impact on the planet, which is the Mother Earth. And more than ever before, the last few decades have seen a lot of policies, a lot of conferences, a lot of awareness regarding how, as engineers and scientists, we should strive to ensure that when we are designing product, it has very, very little impact. Actually, where we're driving at is to actually have zero impact on the earth. So the creation of manufactured products that uses processes that minimizes negative environmental impact, to ensure that we design products that will conserve energy and also conserve the natural resources, and to also be very safe for use by the employees as well. The common practice over the years has been for an engineer or for a scientist is to ensure that it used to be only one way focused: to extract, to process, manufacture, use, and discard. And many of the inventors really don't care so much about what happens after when the items have been discarded. But over the years, there's now a lot of interest in looking into designing for sustainability, wherein designers now have to look into wherein extraction from the earth is less than the replenishment. And replenishing now has to do with a lot of studies are now being conducted with respect to how to reduce waste, to reuse materials, and to recycle. A couple of research have been ongoing in this particular aspect, and I must actually commend many researchers across the globe that are doing research in these various aspects. A sustainable Mother Earth, the question is, does the Earth actually speak? Of course it does. Through the global warming is one of the ways wherein the Earth speaks, with the increase in temperatures across the globe. It's very important to care about the Earth as we carry out our activities. The United Nations also has geared a lot of effort towards promoting sustainable sustainable development goals, encouraging the use of renewable energy sources, and many of the SDGs also relate to, many of the SDGs speaks to sustainability of the Mother Earth. And April 22nd every year has actually been set apart to celebrate the International Mother Earth Day, to reflect on humankind's relationship with the planet, with the earth, and there is an urgency for everyone to get involved, to play our part as we look into providing solutions to problems that we need to solve on Earth, here on Earth. We need to look into how we can conserve the environment and save energy to ensure that we have a sustainable planet. Taking a look into plastics, about 8 million tons of plastics end up in seas and oceans. And the idea around many of the eateries now having recyclable materials for straws and for plates, disposable plates, and all of that is quite encouraging. And where need be, in actual fact, where people can actually do without actually using a straw, maybe take a cup or something as an alternative, has actually also been talked about as well. And plastic dumping in seas, what actually is seen on the surface, it's been researched and told that it is only 5% of the plastic trash that are dumped into the sea across the world. And according to Ocean Conservancy of the US, it says that in actual fact, 95% of used plastics actually submerged beneath the surface of the ocean, where it's actually ends up being a huge problem for aquatic living. Strangles underwater creatures and wrecks the aquatic ecosystem. Still on various advocacies on having a sustainable Mother Earth, Apple plans in 2018 talked about investing over $300 million US into China to have clean energy. Adidas, the footwear, and they are they use a lot of plastics in the majority of their products. They have joined the fight also against plastics, and looking into a lot of research is ongoing at the R&D to consider how to have recyclable plastic materials to actually be able to recycle plastics by 2024. Some basic concepts for each and every one of us to get us thinking, to get us going. We need to consider to look into how to mitigate our impact on the Mother Earth. And you will agree with me that there is a need to actually change our values, our principles, our attitudes, our lifestyles towards many things that we do. And we need to be guided by conservation science, and also look into how we can actually be friendly, to be earth friendly. And some of the impact of the activities of human that we see today speaks in terms of global warming, like I said earlier on, ozone depletion, the loss of biodiversity, and also pollution of air, water, and land. And all of these should get us thinking as researchers. Personal contributions in the field of research. Majorly, I do my research. I started my research in the field of friction stir welding, and then later into additive manufacturing. But one of the key major reasons that attracted me into the field of friction stir welding was the fact that growing up in a remote village in Nigeria, and I saw how welders perform their operations on the streets in Kaba, in a village where I grew up. I used to see the way the films, and they're engulfed in the films of welding along the road, and sometimes I have to visit the welding bays and all of that. And when I was planning to do my doctorate degree at the Nelson Mandela University in South Africa, as I was searching through and looking, I have interest in welding generally, and I was looking into I remembered the idea, the issue around the smoke, the welding fumes and all of that. And then I came across friction stir welding technology and read more about it. And I was really intrigued with the fact that it does not give welding fumes during the welding process. That was actually one major thing that I would say attracted me into the field of friction stir welding. So when I was writing my proposal, I said I would like to work in the field of friction stir welding when I was submitting my proposal to the university. And that was how I got myself into the field. It then became a very interesting technology for me personally, and also I believe to the rest of the world, as this technology has been well embraced by many industries and companies that are reaping a lot of benefits from the field of friction stir welding. Here in the picture here, I have Dr. Wayne Thomas, who is the inventor of the friction stir welding technology. We met in Germany, and that is the Dr. Dos Santos as well in Germany as well. At this point, this picture was taken in 2008, and then I was a PhD candidate in South Africa. And I'm not sure many of the participants, if you are fully aware of the technology invented in 1991 by the Welding Institute in London, and it's a solid state welding technology. So this is a green technology because unlike the conventional welding techniques, it does not give fumes during the welding process. It can be considered as a green technology. And there are no toxic fumes or smoke produced during or after the welding process when compared to the conventional fusion welding technologies. It can also be said that this technology is energy efficient and environmentally friendly as well. The second aspect of research, which I've also had to conduct research in the last 10 years of my career, is in the field of additive manufacturing. I also realized that this is a technology that has come a long way, sustainable, energy efficient at the long run, though capital intensive in setting up. And I collaborate with the Council for Scientific and Industry Research in South Africa, in Pretoria, to conduct my research in the last 10 years over there. Part of the research that I've conducted in this field is looking into mitigating against biofouling, and myself together with some of my students, we conducted research on some biomedical applications, biomedical implants, and also conducted research on the addition of copper to titanium alloys to manipulate the mechanical properties through age hardening to mitigate and prevent biofouling in some materials. Another aspect of research that I've also been into is on biogas digesters for as renewable energy source of gas, source of energy. From this, the biodigesters were built, and the feed were food waste from market in Johannesburg, and the biogas digesters are the research into biogas digesters have been conducted and successful by my research team. Now, I want to quickly talk about interaction between the fourth industrial revolution and the sustainability of the Mother Earth. Across the African continent, the various countries are at various levels. Some are striving in the fourth industrial revolution, while some are still in the second or third industrial revolution. And some countries have also actually had to jump from first to third, and some from second to fourth, as the case may be. The fact remains that there are a lot of benefits to reap from the fourth industrial revolution, and its impact, its footprint regarding its impact on Mother Earth have also been assessed and found to be very, very low. The systems are fully automated, flexible, high speed, high accuracy, and repeatability is also these are part of the benefits of the fourth industrial revolution. This is an aspect of research that has gained a lot of interest in the last few years, less than 5 years, so to speak, on the African continent, and many more research are also still being conducted. But the wake-up call is that as many people find their way into conducting research in the fourth industrial revolution, there is needs to look into the sustainability of the process and also its effect and impact on the Mother Earth. I consider the sustainability of the laser beam additive manufacturing process and friction stir welding technology that I have been engaged with. And I realized that the two processes are sustainable and they have very, very little impact when you look at the life cycle impact assessment of the two technologies. Both of them are they're energy efficient cooling system. They can be considered as a green technology, saves cost at the long run. And looking at the life cycle impact assessment, particularly for the laser beam additive manufacturing, they are known to have very low environmental impact index, low impact on human health, and improve ecosystem quality. So on the fourth industrial revolution and sustainability, its effect on Mother Earth, these are the various aspects of technologies that fourth industrial revolution is looking into: Internet of Things, cyber security, augmented reality, big data analysis, additive manufacturing is one of them, simulation, system integration, and all of that. You will agree with me that all of these put together, speaking to the fourth industrial revolution, they have very, very little less impact on the Mother Earth. There were also a lot of there have been also many people talking about the effect of having masks and all of that on human health. And I've also taken my time to read a lot in that. I'm not a physicist, and I've read a lot about that as well. And I've also been made to realize from published articles that that has been taken care of. That initially the waves were really high, but that has been taken care of over the years with improved research activities. So thank you for your attention. In summary, I've given background and introduction on sustainability and also looking into conducting research, manufacturing technologies, and considering the impact on Mother Earth. Personal contributions to the field of science and engineering were highlighted, and looking into sustainability and the life cycle impacts, environmental impact assessment of those technologies. I also spoke about the fourth industrial revolution and the sustainability of the Mother Earth going forward. So the future direction for us on the African continent, we need to continue to work together, collaborate to provide sustainable solutions to the African continent. And in this, I want to borrow the slang from South Africa, wherein people say amandla, that is power to the people. We can only give power to the people when we work together and we provide sustainable solutions to the African continent and the rest of the world as well. These are some of the references I consulted, especially some of the images that are not personally mine. And I would like to acknowledge some of my sponsors: the African Union Commission, University of Johannesburg, my former employer, the National Science Foundation, a couple of other funders that have supported my research over the last years. And I would like to close by thanking all the participants for joining us in this session and listening to me. And I have a quote from a friend, Professor Satish Kailas of IISc Bangalore. He told me, he said, Esther, you need to have a happy life to even think of being mentally sustainable. That it is when someone is mentally sustainable that the person can actually conduct research that talks about sustainability. He does a lot of research in sustainability of a manufacturing process, and we work together and also supervise some couple of students together as well. This stood out for me, and I took that from him, and I'm recognizing him in this particular talk today. Thank you. So I'm going to unshare quickly. Thank you for your attention. So I'm back into the group, and under Q&A, I do not see any question for Esther. I will type my email address in the general chat box. And is there any quick question for me, or I am good to go? Okay, I see Prof. Matters responding to, I guess you were responding to the picture I took with Dr. Wynne Thomas. I think that was at GKSS. I think that was actually the conference we first met. That should be 2008 or 2009, thereabout. I remember the conference on friction stir welding. Right, you were very, very correct. It was GKSS. And we're holding in our hands the first friction stir weld that was ever made in the whole world. I remember that very, very well. Okay, so participants, thank you very much. I do not see any question for my humble self. I will leave my email address as we move on in this conference, this morning, afternoon, or evening, depending on the part of the world where you are. Okay, so without much ado, I will now call on the next speaker for this session, Professor Nguyen Phi Kim Tha. Pardon me if I did not pronounce your name very, very correctly. I sincerely apologize for that. He is a professor of nanomaterials from the University College London in the UK. He will be presenting on plasmonic and magnetic nanoparticles for biomedical applications. Over to you, Professor Tan. I hope you are in.
Thank you very much. Do you want me to start a video or not?
I think the videos is disabled.
Okay, so that's fine.
Sorry, I think you can share your video if you like.
Okay.
Yes.
So
I have a question I will answer after Professor Tan. So please go ahead, Professor Tan.
Thank you very much. Right, okay. So do you see my slide?
Yes.
Did I share it yet?
Yes.
Oh, okay, you're seeing it, okay.
You only need to activate the slideshow.
Okay, so the slideshow, and if I go to Zoom, I might want to put my face on. I need.
You did earlier on, and then it went back to normal again. You actually activated the slideshow few minutes ago, like a minute ago.
Okay. No, it's in sharing, so I don't understand because you're sharing the screen.
If you look at the bottom right-hand side, you will see the tab to have the slideshow. Usually at the bottom.
Oh, you mean? Oh, yeah.
Yeah.
Okay, I see what I mean. Okay, I can't.
Good. You are good to go.
I can't seem to share the video.
Oh.
Okay. So in any way, I just start my talk. So.
Dr. Esther, you are the host, so you may give the permission to the people to start their videos, or you may be returned back to me, so I can do it on behalf of you. Dr. Esther?
Yeah.
Shane, I think she doesn't have it. Okay, now she's back.
Yes, you are the host, so you may give the permission of starting their videos. Otherwise, you may return to me, and I will do it on behalf of you.
Okay.
Yeah.
Yeah, and also just one comment. I think the question should be left at the end of the session. So
okay,
can we save the time? Yes. Please.
Well, it's up to you because you are the moderators. So it's your boss decision where to manage it.
Yeah, it's fine. We can take all the Q&A after all the presentations.
Sure. Yes.
Okay.
Yes, please. Yes.
Yeah.
So let me know what you want me to start. Okay, when you want me to start.
I'm trying to allow video, but I cannot see. I don't seem to see where. Yeah. So Do you want to check from your side?
No, there is nothing from my side to check. I think because it's not allowed.
Not Prof. Tan. I'm talking about our support, our IT support from
Okay,
WISWB.
Okay, Dr. Shane, can you just hear me, please? If you just, can you just handle it, please?
Okay.
Dr. Shane?
Dr. Shane.
Yeah. Me,
Can-
Tang.
No. I'm just talking to
Yes.
the, yes, please, yes. Dr. Shane, if you can just handle it, please. If you can just like let the Prof. Gwen to share her video, please.
Yes. I'm working on. I will let you know if Doctor, you may just start your video normally, like only pressing, I mean, the icon, the video icon.
Okay. Can you
It's
see?
not working.
It should be beside the mic.
Yes, I
It's
know.
not working.
Yeah.
The videos are not working. You cannot start your video because the host has stopped it. Let's have the presentation from Prof.
Yes.
Tan.
Okay.
Please
Yes.
proceed.
Okay. So let me present now. Okay. So give me a second.
Please remember to activate. Yeah. So please go ahead. You have 15 minutes for your presentation. Thank you.
Okay. So good morning, good day, good evening, everybody, and happy International Women's Day. And probably that, the host didn't have time to look at my profile and he called me him. It's okay. But that is something, it's quite sad because basically we are on the women's in science workshop and the women being called a man is kind of perceivedly in the society, people only think like, professor or speaker, it can only be man. So recordedly in this one, I just want to say that next time anybody write anybody, that be mindful that, women can do the great thing as well. So let me go to start with the science. So today,
Sorry.
Don't worry. It is unconsidered by us, don't worry. So I'm just talk about the plasmonic and magnetic nanoparticle for healthcare application. I understand that we have only very short time. So actually through this talk, it's going to be recording, giving you a lot of resources that you can continue to have more of my presentation through the different media or recorded resources. So that I'm going to be very fast. So I'm just want to say that, I'm based at the Royal Institution. It is founded in 1799. It's an audit independent research laboratory in the world where they have a higher concentration of Nobel laureate per meter square and also discover the 10 elements. So it's a really great place, it's inspiring place to do science. So I really hope that because we are now in giving this talk to inspire people. So I hope that, the talk will be inspiring for people following on and doing science. So just give you a couple of very famous, well-known names. So like Michael Faraday and so John Tyndall. I possibly have time to show you some John Tyndall effect and the DIWA, where you are hot and cold, you keep this liquid nitrogen or hot water tea jug they invented by James Dewar. And if you work in the area of nanotechnology, then with nanoparticle, you need to characterize by XRD. So, there at the Royal Institution, you have a father and son bracket. Okay, so here I'm going to give you a lot more resources. So for example, nanoparticle team issue, it was edited to celebrate 350-year anniversary of the Royal Society. And you can also look into the Royal Society library. And also here, if you Google search for Royal Society science story, and the story called Small for nanotechnology, and you can also have a video to watch. So the next thing is that I give you a really interesting historic sample, and this is made by Michael Faraday in 1855. And then in 1856, he published a paper. It's a peer-reviewed paper of almost, for me, that early day of nanoparticle research. So when you're talking about nanotechnology, actually it's not new, but in this day, he called it like fine particle, okay? So again, I gave a public lecture, and it's called Nanomaterial Tackling the Global Health Challenges. So if you also Google this term, or you go into the YouTube and you Google Professor Tang Nanomaterials, you will jump into this 1 hour lunchtime lecture that where you can have a lot more detail. So here it is great because I also show some demonstration of how the nanoparticle were made. And so I just give you here a very simple way of how a nanoparticle can be made. So you have a gold salt here, and here this is a lemon root because it's citrate, and then after cooking or heating, you form this gold nanoparticle. With over time, you can see the color change, and you form the nanoparticle you observe with high electron density. Okay, so you have a different nanoparticles size, and they will have a different color because they absorb light at a different wavelength. Okay, so something I'm going to give as an application. So because gold nanoparticle going to interact with light with electromagnetic wave, and you will have this typical absorption peak, but then it's going to aggregate. Then you will see that the absorption increase as the longer wavelength, and the color change from red to blue because it absorbs at the different wavelengths. So one of the application, so we look at like the immunoassay, and in relation, for example, now we talk about the COVID. So if you got nanoparticle and you're going to have some ligand surrounding it, and you could detect like spike protein in the COVID, and then it's going to interact with the antibody, provided that you got antibody coated with gold nanoparticle. And then you're going to see that the color of the solution change from red to blue. So I wrote a review on the current detection of the COVID-19, and here is also one of the technique that people using to visualize the detection of if you have COVID or not. So this work is very highly cited, so it's very applicable, and I'm very mindful that a lot of colleagues from a developing country where you don't have a lot of equipment, for example, when you want to look at the nanoparticle as I have shown earlier with the TM image, then you need to have a very expensive equipment with highly trained personnel. But in this case, you can now using the UVVs, so very simple spectrometer that you could find out the absorption, and you got the absorption, and then you have the here's the absorption at 450 nanometers. You do the ratio, and provided your nanoparticle, if the position is monodispersed, then you can find out the size of the nanoparticle. And now it's nearly 3,000 citation. So this is very applicable for you in developing country. If you make gold nanoparticle, you can determine the size. So one, you know the size. How you know the concentration of nanoparticle? Because you could have many application. So now you know the size, and then from this table you can see the actination coefficient, and based on the different actination coefficient, you can calculate the concentration of the nanoparticle because based on absorption from UVVs, based on the epsilon from the table and from the side you found previously, you can find the concentration of the nanoparticle. So it's very, very useful. So the next thing, I also want to inspire and update the most recent work. So you're aware that, apart from the gold spherical, you can also make very monodispersed gold nanorod. And what with the gold nanorod is that, like here, you only see one shape is rod, and it is not a mix of the different shape, but also have a very fine-tuned aspect ratio. And then you can see the absorption very tightly here. So the library of the gold nanorod is very fine-tuned. And what is the application? So again, as I said, that go through the different video and lecture I gave previously, you will give a lot more detail about the work. I got very short time, so I'm giving something which is very contemporary and it have a lot of application that you think that either in developed country or developing countries, you can see that, the surface is very important. We're talking about like when you go to public transport, if you happen to touch your nose and your hand going to touch into the handrail of the tube, the train or the bus, and then you're going to transmit the virus. So if this surface can be covered with a polymer, and polymer now going to embed it with gold nanoparticles, and gold nanoparticle interact with a dye called the crystal violets, and it forming rod reactive oxygen species, and it kill the virus. In this case, I have to say that this study was shown that it killed the bacteria, but it's inspiringly that one of my students from Egypt, and she said that I would like to try this one on COVID, but I said, okay, you can do that, but finish your PhD first, because, she got a different subject. So that is that inspiring you for something that you could study in your own space. So now I'm moving on a little bit with magnetic nanoparticles. So Michael Friday, he made this homemade by himself, the ring coil apparatus, where he studied the interaction between electricity and magnetism. So again, I'm giving you a lot of resources in this talk rather than giving the talk itself. So basically here, there are 2 books. So it's about magnetic nanoparticle with for different application and in the focus on the clinical aspect area. So these 2 books are complementary. So the 2 volumes, so you could order it and ask your library to order electronic copy, so it is cheaper, and you also can order the chapter by chapter, so that is interest to you. So this is a very more recent work where we make the magnetic nanoparticle and to make it very highly magnetic, so you have a really high magnetic moment where all the magnetic application relies on the magnetization of the nanoparticle. So the iron is giving you very high magnetic moment, but it get oxidized into the iron oxide, right? So iron oxide will reduce the magnetic moment going down. So we made the synthesis that we keep the iron and let the oxidation, which it cannot preventable, let it grow and protect the nanoparticle. And we study the saturation magnetization, and it is very high, and compared with the commercial available magnetic nanoparticle, our nanoparticle have a higher heating capability, measuring by the value called INP, intrinsic loss parameter, but basically to say that, it hitting better, and they also stable for 2 months. So it also other thing that you could make, for example, here you can have the iron oxide nanoparticle and you coat it with gold nanoparticle. So you think about the plasmonic property previously, and now we got a magnetic. So you have a dual property, magnetic and plasmonic combined together, because the gold nanoparticle research, you have a vast literature. You can very easily in first survey functionalize. So this work also got really highly cited, like maybe over 150 citation. Again, I'm just giving you one example, which is very relevant in the developing countries. So you could use a magnetic nanoparticle and you can use that to pull the bacteria, right? So infectious disease is a problem not only, in developing country, it's also in developed country, but in developing country where you have the problem with the water source. So for example, cholera. So this, it is more problem. So you can think about that you can use this magnetic nanoparticle, you can pull the bacteria down, you can higher concentration, you can detect it early. So you can, determine that the contaminated drinking water source, for example. So other application, I just give you example, like using magnetic nanoparticle for hyperthermia cancer treatment. So this is a very exciting area that where it's now already have a patient in the clinic. The machine have been now launched around Europe, and they got the particle for FDA approved. So it's going to go into the mainstream of one area that they can use in the complementary with an existing area for cancer treatment. So how does it work? So you have a magnetic nanoparticle, you're using alternating magnetic field, and the alternating magnetic field is going to heat up your nanoparticle. The nanoparticle going to heat up the tumor, cancer or tumor in the localized region. So you only kill the infected area. So you're not going to have a side effect of the whole body. Okay, so then we also cleverly designed the system that we also have a drug. So the blue dot here is a drug, it's a doxorubicin, is that the classical traditional drug to kill the cancer cell. So what you're going to do that you have a synergistic effect of the heating, hyperthermia cancer treatment, and also the drug. So we look into the profile of the drug release, and here that we have a nanoparticle, we co-polymerize them, grafting them, and then we're loading the drug around here, these polymer contracts. So the system we designed that when in the cancer cell is more acidic, and it breaks the bond and it releases the drug. So that means it's a normal cell, you don't have the drug, so you don't have a side effect. And also you're heating up. At the higher temperature, you have the higher release because the open up the structure of the polymer. So you have a dual switch. That means you only switch when the particle get inside the cancer cell, but you only also treat it when you're heating up by using alternating magnetic fields. Okay, so we use also another very new research area for us in the last 5 years is that using microfluidic to synthesis of the nanoparticle, because the traditional way you synthesize in the bottle, we call it batch, it doesn't allow you to control the mixing, the nucleation, or the growth, so and also functionalization of nanoparticles. So it's also here as new area, because oftentimes you go to the conference and you want to look for what is the upcoming area, what is a new thing. So I would inspire you to think about a different new research area as well. So using this microfluidic method, we could form very high magnetic moment iron carbide, and then we have a core cell structure and we characterize them and using them also for hyperthermia. So another area that you can look at is that here you're talking about magnetic hyperthermia here, but there is also another area that you can use a laser, and the laser going to heat up the gold nano rod. As I mentioned early on, the rod going to heat up the cancer cell, similarly with the magnetic nanoparticle. So you have a different facility for you to deploy different technology. So let's say you have a big hospital where you can have a big magnetic machine where you could use a magnetic hyperthermia treatment. But let's say that you are in the provincial clinic where you have less resources, and then you could use a laser source because they are very small, portable, and you can use a gold nanorod here to kill the cancer cell. Okay, so I was very privileged, and I'm very humble and honored to get the Rosalind Franklin Award from the Royal Society. It is National Academy of Science in UK, and I gave 1 hour public lecture from nanomaterial for the bedside. And here, this is recorded, so you can have the link, or you can just Google it, like Franklin lecture 2019, nanomaterial for bedside. You have another hour of my talk. So now I'm just giving you the very latest work that published in December last year, that we have now combined here the magnetic nanoparticle, but also with doxorubicin. So what's the difference with this work and the previous work? So we look into that if this doxorubicin is stay outside of the cell or they get inside of the cell here, what is the difference? So the difference is that, like, you could kill the cancer cell, you don't need to have this drug or nanoparticle get inside the cell. So that means it's quite effective, it's quite simple. And also from the work, it shows that you only need to raise the temperature out to 40 degrees. You also already effective of killing the cancer cell. And by the way, all of you listen to the talk that my works would be, I would say 90% are open access. That means you can go to my website, you can download the paper for free, because we are lucky to be in UK. My work has been funded by EPRC, so they support the open access. You can get all of that. So with that, I would like to thank all my collaborators, and it's also from people from developing countries, and you know, it is very interdisciplinary as well. So I would like to thank all the different funding agencies from different countries as well. And I am now the editor-in-chief of the Royal Society of Chemistry book series. So if you would like to edit book in this area of nanotechnology, please drop me a line. And with that, I would like to thank you very much for your attention. And you know, I would really looking forward to your question and comment either now or later in the section. Thank you very much.
Thank you, Professor Tan, for your very inspiring presentation on nanoparticles, absorption and concentration of nanoparticles, your case studies of some of the work that you have done, and also on magnetic nanoparticles as well. So intriguing, and really appreciate you to sharing your talk with all the participants there this day. So if you please on share, we'll be looking into if you can have access to the Q&A, you can answer some of the questions in there live. Otherwise, when we are through with all the presenters, we can then take some of the questions and answers. We have 2 more presenters for this session, and we are not doing well with time. I want to implore that the presenters should please keep to time, 15 minutes allocated to you, as I would not like to obstruct you while you are talking.
Dr. Esther, if I may say something.
Okay.
Dr. Ahmed Munam, who is the next presenter, is not. I cannot see him in the panelist, and I do also apologize to all of you because there has been a mistake in the setting of the session, in which we disabled opening or sharing the videos. That's why I couldn't back to you and tell you that you can now have your videos. So I think on this way there's only one remaining speaker.
Oh, good.
So can I also mention for the technical team that the Q&A, I couldn't access the Q&A as well.
Okay.
Okay.
Can you please give access to all the panelists to be able to access the Q&A and be able to answer some questions? Although all the comments and questions there.
Yeah.
Okay, I think it's okay now.
Yeah, I think they might able. Yeah.
Yeah, thank you. So
Yeah.
instead, there was some question here because we don't have the next speaker. I would like to answer Bibi Mabonzu. I don't know if he can speak or I can read it for him. In which field is this technology used in Africa? You can feel, could I answer him this question for Bibi, he or her? Is Bibi Mabunzo? It's just like in which field, so it can be many different fields of the technology of nanotechnology. And I mentioned before that you can take care about healthcare. So regardless where you're from, you have a cancer. So that not discriminate you wherever you're Africa or Asia. So, you know, in the healthcare, in the environment, so you can use the technology for water purification, you taking care of the wastewater, and also it's an environmental, that's the environmental aspect. They also, not in my research area, but I know that it's also using for the energy, you know, the battery technology, also for catalysis technology. So, you know, so nanotechnology is cover all area that could be used for Africa. So I hope that I answer your question, but if not clear, please write again. Please receive your slide on communication to somebody in France, Mariam Mabunzo. Yes, so I don't know what is a policy, but basically it's recorded. So I think that the organizer will share this recording to people, and I'm deliberately making it very widely accessed to the people. So somebody asking me to send the slide, but I think the organizer are going to do that for everybody. Is that correct?
Yes, it's
Okay.
like, yeah, the recordings are on YouTube and will be shared as well. So
Yes.
So
yeah.
so you have that. So you have that available. So yeah, so no more question for me. So you know, I hand it over to the organizer.
Thank you, Prof. Tan. Thank you very much. Really appreciate. I also see that this person BB was also asking about the friction stir welding technology, where it's being used in Africa. Majorly, I know that there's a company in Cape Town that is using the friction stir welding technology for tank to produce big tanks in Cape Town. And I know that I think some companies in Northern Africa, Morocco, Algeria also uses friction stir welding technology.
Yeah.
And I think it's also in Egypt as well that the technology is also being used. So on this note, thank you very much. Prof. Tan, can you please?
Thank you,
Yeah.
thank you, the
Thank
chair.
you, Prof.
Thank
Tan.
you, Chair.
All right, can you please stop sharing your slides?
Yes.
Right at the top, you will see
yes,
stop.
I did it.
All
I
right.
did it.
Yeah,
Stop
yeah.
it. Yeah.
Thank you. Thank you very much. So we will now take the last speaker, since we do not have Dr. Ahmed Monet join us. We'll be taking the last speaker for this session, Dr. Taha Al-Rashid. He is from the Technology University, Iraq, and he will be speaking on a topic, preparation and characterization of colloidal gold zinc oxide nanocomposites via laser ablation in deionized water and study their antioxidant activities. Over to you, Dr. Al-Rashid. Thank you.
Yes, sir. Good afternoon, good morning for everyone. I
Good day
hope
to
you are doing well, everybody here. Actually, I thank you for all organization and all person here. Today, I'm going to share my presentation. My say is okay?
Yes, you need
Yeah.
to activate your slideshow. Thank
Yeah.
you.
Yeah.
Yeah.
Now I think it's good. Yeah. So my presentation about synthesis of IU and ZNO nanoparticles and study their biomedical application. As you can see, when preparation the nanoparticles, there are many methods for preparation it, and for a more application for nanoparticles and the methods, it's so important when it's the method is more eco-friendly and safety and it's low cost. As you see the scale for nanoparticles, this region will more study about the size. So because more using and more useful for more application at biomedical and photocatalyst and whatever. So all our research about this region, as I can see, the more useful. And there are many methods for preparation nanocomposite, say, for semiconductor and metal, but the pulse laser ablation and liquid, this are more safety and low cost and very simple to preparation than nanoparticles. So the experimental work, we prepared the ZNO and gold nanoparticles as a disk and putting on the beaker for 3 milliliter of liquid water and checking for the pulse laser. As you see, the mechanism for ablation and the interaction between of the irradiation and the target, and generated a small size for the metal and nanoparticle of the gold or ZNO. So this also shows through the preparation. As you can see, this plasma and shocking for irradiation by laser and target. And these samples are result for all the preparation. As you can see, this gold nanoparticles, and this difference between of the colors is dependent on the energy and some parameters. Also, these samples for ZNO. Also, you can see the difference between of the colors, as I can see the depending on the energy and pulses and whatever. So after I'm prepared the nanoparticles, we application on the antioxidant activity and measure the DPPH assay. The colloidal of AU and ZNO composite was evaluated for the DPPH scavening activities. Each particles were mixing with the DPPH solution, and then absolute ethanol was added to reach a volume of 0.5 ml. The sample were kept in the dark for 30 minutes at 37 centigrade. The optical density for sample was measured at 517 nanometers. The percentage of the scavening activity of the prepared nanoparticle was measured using the formula. As you can see, this formula, we measure the optical density and calculate the scavening and DPPH assay independent on the statistical analysis, as you can see the graph at present. So this diagram show you the parameter and all the conditions to preparation it. Firstly, we prepared the zinc immersed in Dionese water and focusing on 200 pulse, and also same methods for prepare the AU. After we're mixing together, we irradiated by post laser at 532 nanometer and doing all the characterization, TM and UV. Also, some characterizing not mentioned here. And finally, the antioxidants. So, as you can see, this absorption for for AU nanoparticles and ZNO nanoparticles, and this figure, this line show the mixing for AU and ZNO nanocomposites. If the absorption will be decreased to 0.15 when mixing and when irradiated by post laser application. So this diagram also show the FTIR, all the ligand and peaks show the interaction or adhesive between of ZNO and AU. Also, this show the band gap for ZNO and AU and AU ZNO. So this TM image show the pure ZNO and pure AU, and when mixing together, as you can see, that as show you. As you can see, this region when adherent between the ZNO and AU, the average size of ZNO is 14 nanometers, and when the most spherical from when the average size also for AU 35 nanometers. So after we're prepared all the parameter and mixing together, we go to the application. Our application, as I mentioned, to antioxidant, and that sounds so antioxidant, and I think there are a problem. Okay, so this diagram shows the antioxidant for ZNO, pure ZNO, and sorry, pure AU and pure ZNO, and as you can see, this mixing. So the more efficient and more killing for antioxidant for bacterial and optical density when mixing together is a good result when mixing AU and ZNO, also when irradiated by the second harmonic laser. So the conclusion in this study, a basic laser simple method was used to create pure nanocomposites like AU and ZNO and AU ZNO nanocomposite, and the second harmonic laser was also used to minimize the mixing. Anyone maybe ask why we are using the second harmonic laser. This answer to you to minimize the size of particle after preparation as little as possible, where we were able to understand the phase of AU, ZNO nanocomposite based on the interaction of the laser light within the colloidal solution. The UV visible tests are characterized by reporter formation and clearly indicates AU and ZNO nanocomposite and demonstrated the interaction mechanism of ZNO and AU surface. These nanoparticles have ability to scavening free radicals. So thank you for listening and thank you for all the organization. Thanks a lot.
Thank you very much, Dr. Al-Rashid, for your very wonderful presentation on the analysis of the absorption and study into antioxidants of the gold zinc oxide nanocomposite. Really appreciate your presentation and coming on board this afternoon to present to all the participants. So yeah, you can please unshare your slides. I'm not sure if there are any specific questions for Dr. Al-Rashid. The questions in the Q&A have been answered, and I'm not seeing any further question. So is there any one quick question, input, or comment that anyone would like to make on the Q&A platform before we bring this session to a close? I would like to ask the support to me as a moderator, Dr. Jalal. Do
Yes,
you have
I'm here.
anything to say? Yeah. Do you
Yeah,
have
thank
anything
you.
to say? Yeah.
So I just want to share just this for the people if they have like any question to be asked. So just to see the speakers if they want to remember like any question to be asked. So that's all from my side, and thank you very much.
All right. Thank you very much, Dr.
And
Jalal.
do you see the slide I shared with you?
Yes, we can
Okay.
see your slide, but we don't have the email addresses. I know.
Just for
Yeah.
like, just to remember the people, yes.
Oh, okay. So, Dr. Al-Rashid, if you can please leave your.
Excuse me.
Yes,
Excuse me.
sir, I hear you.
All sessions are on Facebook and YouTube so that you can watch it later.
Okay. Okay.
Okay.
All right. Thank you very much.
Thanks a lot.
So, yeah, if we can have all the presenters, if you would like to, if you are open to collaboration, you please leave your email address on the chat box for other participants to take note and then send any email through to you. So, Dr. Jalal, in the absence of no other business, can we now bring this session to a close, or is there anything else that?
No, that's all. Thank you very much to all the presenters and the participants, and thank you to the moderators, to you too, and thank you very much. That's from all my side, from my side.
All right.
Am I correct?
Okay. Thank you from my side. I want to thank you all, to all the panelists, for the wonderful talks, very interesting, and thank you to all the panelists, and thanks to all the participants that joined us in this parallel session. Wishing you all the best for the remaining part of the conference. On this note, thank you. Bye-bye.
I thank you, Dr. Ashtar, for moderating the session.
Thank you. Thank you,
Yep.
Dr. Taha. Thank you. Bye-bye.
Thank you so much. Bye-bye.
Bye.